What's up? Welcome. I received a comment, so I posted a video about my idea for the concept that there's gravitational lensing along the edge of the slit of the double slit experiment, so that passing particles are gravitationally lensed so that their resulting position depends on the position that they go through the slit, effectively producing a wave cumulatively from particles passing through essentially all parts of the slit, or a distribution of the slit that leads to that. And I got a comment that's just a link to this video, and I start watching it, and I decide, well, maybe I'll just I notice also it's a whole lecture series. This is MIT open courseware available online for their courses, which is cool. Find course topics. So I was looking at courses, find courses, topics. Went, of course, to science, physics, and then quantum mechanics, because as I started to watch this video, I was just like, what are they talking about? Like, where did this come from? And is this like the first lecture? And I figured, well, there must be something before this. So I went to the course list, and I found it 8.04, thinking 8 meant maybe there were other courses before it, or 0.04. But it says this course covers the experimental basis of quantum physics. It introduces wave mechanics, Schrodinger's equation in a single dimension, and Schrodinger's equation in 3 dimensions. It is the first course in the undergraduate quantum physics sequence, followed by quantum physics 2 and 3. So this is an undergraduate course. So I'm just going to start watching it.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
By the way, this is just cool that lectures at this point are online like this. And honestly, like, why wouldn't we do it this way? It's much more efficient. It's more accessible. It doesn't cost so much. It's not such a burden on society to have to go to class. And I mean, certainly it has its benefits, but this way, it's so much easier and cheaper and just more efficient. So I like that this is online. And maybe if the school wasn't so rich, it would make sense to donate. In the future, there may come a time when schools really do start to struggle. Because, I mean, they take in so much tuition. It's crazy to even suggest that they need money. When they suggest, like, ask for donations from alumni and things, it's like, you guys got a lot of income. What are you doing with it? To be needing more like that?
Hi, everyone.
Anyway.
Hi. Welcome to 804 for spring 2013. This is the fourth and presumably final time that I will be teaching this class, so I'm pretty excited about it. So my name is Alan Adams. I'll be lecturing the course. I'm an assistant professor in course 8. I study string theory and its applications to gravity, quantum gravity, and condensed matter physics. Quantum mechanics. This is a course in quantum mechanics. Quantum mechanics is my daily language. Quantum mechanics is my old friend. I met quantum mechanics 20 years ago. I just realized that last night. It was kind of depressing. So, old friend. It's also my most powerful tool. So I'm pretty psyched about it. Our recitation instructors are Barton Zwiebach, yay, and Matt Evans, yay. Okay, Matt's new to the department, so welcome him. Hi. So he just started his faculty position, which is pretty awesome. And our TA is Paolo Glorioso. Paolo, are you here? Hey, there you are. Okay, so he's a person to send all complaints to. So just out of curiosity, how many of y'all are course 8? Oh, awesome. How many of y'all are, I don't know, 18? Solid? 6? Excellent. 9? No one? Damn, this is the first year we haven't had anyone course 9. That's a shame. Last year one of the best students was a course 9 student. So 2 practical things to know. The first thing is everything that we put out will be on the Stellar website. Lecture notes, homeworks, exams, everything is going to be done through Stellar, including your grades. The second thing is that, as you may...
All right, that's fine where he actually starts talking.
Are there any other practical questions? Yeah?
Did you say it was a latest policy?
Latest policy. No late work is accepted whatsoever. They're alone. It's going to be an introduction to a basic idea that is going to haunt, plague, and charm us through the rest of the semester. Okay? Problem set. Cool. Others? Okay. So the first lecture, the content of the physics of the first lecture is relatively standalone. It's going to be an introduction to a basic idea that is going to haunt, plague, and charm us through the rest of the semester. Okay? The logic of this lecture is based on a very beautiful discussion in the first few chapters of a book by David Albert called Quantum Mechanics and Experience. It's a book for philosophers, but the first few chapters are really lovely introduction at a non-technical level, and I encourage you to take a look at them because they're very lovely. But it's, to be sure, straight up physics. Okay. Ready? I love this stuff. So today I want to describe to you a particular set of experiments. Now, to my mind, these are the most unsettling experiments ever done. These experiments involve electrons. They have been performed, and the results, as I will describe them, are true. I'm going to focus on 2 properties of electrons. I will call them color and hardness. Okay? And these are not the technical names. We'll learn the technical names for these properties later on in the semester, but to avoid distracting you by preconceived notions of what these things mean, I'm going to use ambiguous labels, color and hardness. And the empirical fact
This is a problem when this is how it's taught. It's like, what the hell is color and hardness? So I started watching this. I'm like, color. And then he says white and black. I'm like, okay, so we see color because you can...
is that every electron that's ever been observed is either black or white and no other color. We've never seen a blue electron. There are no green electrons. No one has ever found a fluorescent.
So he's presenting it like color is color. So I'm just like, what? So I start looking around and I find this one. And it's the same way. We will discuss the story is about 2 physical properties of electrons that we can measure with great accuracy. The precise physical definitions of these properties will not matter. They do, however, correspond to real properties of electrons or photons, as we shall see later. And then they just say, okay, it can be these things. And then for electrons, these hardness and color boxes are called a Stern-Gerlock apparatus, which is a region of non-uniform magnetic field. Something of actual input of what they're talking about. Like, we put it into a box and it chooses if it's hard or soft, and like, how? What is the process? Why is this, like, every time we do it and we get hard or soft? And then I start looking around more and I find they do this experiment where they shine electrons past magnets and it separates. Electrons possess two valued spin properties. With respect to a given direction, an electron can possess either the value spin up or the value spin down. There are as many of these spin properties as there are possible axes. For simplicity, call two such spin properties color with values white and black, and hardness with values hard and soft. And then they just go into it like hard and soft, color, experiment, color. We can build a hardness measuring box. Or can we? Can we determine which electrons get their color values? And just, it's lost what is actually even going on anymore to even try to present some, like, maybe it's this, because they're not describing what's actually happening. So, like, somewhere in this document, classical. Any reputable classical physicist would say at this point that electrons entering the last so in this experiment, I'll come back to this after he talks about it.
Electron. They're either black or they are white. It is a binary property.
So mind you, it's not black or white, it's something related to spin, which is relating to how it functions in a magnetic field. That's what they're really measuring. It's interaction with a particular magnetic field, and whether it goes this way or that way, and noticing that it does go this way or that way. But to call it color and then hardness, like, this is so confusing. And notice he starts off Quantum Physics 1, first lecture, color and hardness. These things just exist. And so my mind listening to this, I'm like, so we observe color when we look at electrons, we're able to see color and we only see black and white. But notice he says black or white. This one says magenta or some other color, green. And so they're just picking two colors to represent, like, the two opposites of this, like, spin motion that's happening, resulting in actual differentiation in the paths that they take. Because this is what matters. Like, what's going on here? When they start confusing it by, like, saying, okay, there's a box, and then in that box we decide we see if its color is black or white.
Secondly, their hardness is either hard or soft. They are never squishy. No one's ever found one that dribbles. They are either hard or they are soft. Binary properties. Okay? Now, what I mean by this is that it is possible to build a device which measures the color and the hardness. In particular, it is possible to build a box, which I will call a color box, that measures the color. And the way it works is this. It has 3 apertures, an in port and 2 out ports, one which sends out black electrons and one which sends out white electrons. Okay? And the utility of this box is that the color can be inferred from the position. If you find the particle, the electron over here, it is a white electron. If you find the electron here, it is a black electron. Cool? Similarly, we can build a hardness box, which again has 3 apertures, an in port, and hard electrons come out this port, and soft electrons come out this port. Okay? Now, if you want, you're free to imagine that these boxes are built by putting, a monkey inside, and you send in an electron.
A monkey? Dude, like, how does this device that's producing this result work? It's not a monkey. It's essentially saying it doesn't matter how we do it. It just has this result every time. But, like, what are you guys doing to get this result? Matters, obviously. Like, this is just what happens, and then we don't even pay attention to what the experiment actually is, and just are like, hard electrons are hard or soft, they have color. It's like completely loses its actual basis in observation. It's just like, whoa.
And the monkey, with the ears, looks at the electron and says, it's a hard electron, it sends it out one way, or it's a soft electron, it sends out the other. The workings inside do not matter. And in particular, later in the semester, I will describe in considerable detail the workings inside this apparatus. And here's something I want to emphasize to you. It can be built in principle.
Why not now? Like, right now would be when to explain this. Because this is clearly misunderstood. I don't know what they're doing to even guess at it. From what I've looked at, if it's spin related and going through magnetic fields and that are probably just like dissecting flows. I could see how it could lose its memory of something and become something else. It's just, there's no information. It's just hard and color. And it appears like this is kind of just how it's taught. Like, very...
using monkeys, hyper-intelligent monkeys that can see electrons. It could also be built using...
All is one.
Using magnets and silver atoms. It can be done with neutrons. It can be done with all sorts of different technologies. And they all give precisely the same results as I'm about to describe. Okay? They all give precisely the same results. And...
I mean, listen to that list again.
You send in an electron, and the monkey, with the ears, looks at the electron and says, it's a hard electron, it sends it out one way, or it's a soft electron, it sends out the other. The workings inside do not matter. And in particular, later in the semester, I will describe in considerable detail the workings inside this apparatus. And here's something I want to emphasize to you. It can be built in principle using monkeys, hyper-intelligent monkeys that can see electrons. It could also be built using magnets and silver atoms. It can be done with neutrons. It can be done with all sorts of different technologies. And they all give precisely the same results as I'm about to describe.
Magnets and silver atoms. I mean, Specifics matter. And when we start saying color and hardness and like using it as just a term, and it's just like, this is so detached from reality. Like me.
Okay? They all give precisely the same results. So it does not matter what's inside, but if you want a little idea, you can imagine putting a monkey inside, a hyper-intelligent monkey.
Or I could imagine like the actual technique would be nice. Like to teach this to unsuspecting children or adults, whatever, unsuspecting people. And just jump over why we think it and just, oh yeah, we think this now. We'll come back to why, but just hardness and color, they're things. Even though they're related to... It's... Like, that's not even a thing in physics. Hardness and color. To do something like that. That would be like saying the Earth's rotation is like yellow because it spins in the direction that it spins, so it's a yellow rotation. So there's yellow rotations and green rotations, and all we've ever seen is yellow and green rotations. What the fuck? Why don't you just say the thing that it is? Like, he said something about spin, like that at least is some physical like rotation of a body. That maybe that's some like accurate, like maybe that's like down the path of what's happening rather than color. It's not like it's
I don't know, it sounds good. So I'm going to call, So a key property of these hardness boxes and color boxes is that they are repeatable. And here's what I mean by that. If I send in an electron and I find that it comes out of a color box black, and then I send it in again, then if I send it into another color box, it comes out black again. So in diagrams, if I send in some random electron to a color box and I discover that it comes out, let's say, the white aperture, and so here's...
So if I send an electron into some kind of device that influences and separates the electrons based on their spin, based on their physical rotation relative to the flow of the ether they're passing through, then it will have a spin, and that is similar or the same in the same angle of rotation, the same axes. If it comes out this side, and the opposite if it comes out the other side. Like something like that, it makes more sense than just saying into a color box that separates black and white electrons. Like,
and I take the ones that come out the white aperture and I send them into a color box again, then with 100% confidence, 100% of the time, the electron coming out of the white port incident on the color box will come out the white aperture again. And 0% of the time will it come out the black aperture. So this is a persistent property. You notice that it's white. You measure it again, it's still white. Do it a little bit later, it's still white. Okay? It's a persistent property. Ditto the hardness. If I send in a bunch of electrons into a hardness box, here's an important thing. Well, sending them into a hardness box, and I take out the ones that come out soft.
which by the way is just spin in a different axis. So like color and hardness suggest they're different features, but they're really just the same thing. Something relating to its motion relative to the environment that it's passing through, in terms of which way it's rotating.
And I send them again into a hardness box, and they come out soft. They will come out.
So these two are the same experiment repeated. So whatever separation technique they do causes it to not be influenced the second time, because it doesn't change their motions. Maybe it's all kind of like the same slices. I don't know. And then they do it a different way, probably the same exact experiment, but just like a different angle, it sounds like. Like the field is in the parallel to the ground rather than perpendicular or something, like. And then is color and hardness.
Come out soft with 100% confidence, 100% of the time. Never do they come out the hard aperture.
So he's saying if they come out if they come out white, and then they do it again through another color box, they come out white again 100% of the time in the second color box. Same thing happens for hardness. If it comes out soft 100% through another hardness box, go soft, meaning maintain the same spin essentially. I guess something about the process means that their spin is the same and isn't influenced differently a second time through this system to make it so some of them become the other kind.
Okay? Any questions at this point? So here's a natural question. Might the color and the hardness of an electron be related? And more precisely,
My natural question at this point was, what the fuck are you talking about? What experiments? Oh my god.
might they be correlated? Might knowing the color infer something about the hardness? So for example, so being male and being a bachelor are correlated properties, because if you're male, you don't know if you're a bachelor or not, but if you're a bachelor, you're male. That's the definition of the word. Right? So is it possible that color and hardness are similarly correlated? So, I don't know, there are lots of good examples, like wearing a red shirt and beaming down to the surface and making it back to the Enterprise later after the away team returns. Correlated, right? Negatively, but correlated. So the question is, suppose, e.g., suppose we know that an electron is white. Does that determine the hardness? So we can answer this question by using our boxes.
The question is just void of meaning when it's unrelated to the spin that actually, or whatever it is. I mean, I don't even know if the spin is spin because they're saying spin, but you know, it could be like the same as color, where it just like doesn't actually have any like meaning that's attached to like a word. So when you say color, you mean spin? And when you say hardness, you mean spin. And when you say spin, you mean what now? Color? When you say spin, you mean color? Like, what the Seems circular. I mean, it must be something's actual physical rotation of the body relative to its environment. For us to arrive at the, even like the images like of spin along an axis.
Yeah. So here's what I'm going to do. I'm going to take some random set of electrons. Oops, that's not random. Random. And I'm going to send them into a color box. And I'm going to take the electrons that come out the wide aperture. And here's a useful fact. When I say random, here's operationally what I mean. I take some piece of material, I scrape it, I pull off some electrons, and they're totally randomly chosen from the material, and I send them in. If I send a random pile of electrons into a color box, useful thing to know, they come out about half and half. It's just some random assortment. Some of them white, some of them come out black. Suppose I send some random collection of electrons into a color box, and I take those which come out the white aperture. And I want to know, does white determine hardness? So I can do that, check, by then sending these white electrons into a hardness box and seeing what comes out. Hard, soft. And what we find is that 50% of those electrons incident on the hardness box come out hard. And 50% come out soft. Okay? And ditto if we reverse this. If we take hardness and take, for example, a soft electron and send it into a color box, we again get 50-50. Okay? So if you take a white electron, you send it into a hardness box, you're at even odds. You're at chance as to whether it's going to come out hard or soft. And similarly, if you send
as if it's random, which would perhaps be the case if it was different orientations.
A soft electron into a color box, even odds it's going to come out black or white. Okay? So knowing the hardness does not give you any information about the color. And knowing the color does not give you any information about the hardness.
Facts. No, that's the truth.
Cool? These are independent facts.
I concur.
Independent properties. They're not correlated in this sense, in precisely this operational sense. Cool? Questions?
Why are we talking about the color for the electron? The silence for the class. Everyone's just like, they seem color. I guess fucking color then.
Okay. So measuring the color gives 0 predictive power for the hardness, and measuring the hardness gives 0 predictive power for the color. And from that I will say that these properties are uncorrelated. So H, hardness, and color are in this sense uncorrelated. So using these properties of the color and hardness boxes, I want to run a few more experiments. I want to probe these properties of color and hardness a little more. And in particular, knowing these results allows us...
This is such a problem when this is how it's talked about. So for like trying to understand it, like, well, color and hardness are blah, 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 blah. Like, you gotta dig through all these layers to actually get to the meat of what is happening. Like,
just to make predictions to predict the results for a set of very simple experiments. Now what we're going to do for the next bit is we're going to run some simple experiments, and we're going to make predictions, and then those simple experiments are going to lead us to more complicated experiments. But let's make sure we understand the simple ones first. So for example, let's take this last experiment, color hardness, and let's add a color box. One more monkey. So color in
I mean, but it makes no sense. You can't just say monkeys. Like, fucking monkeys could do it, but they're not doing it. It's a fucking field, man. You know, like a environment that's influencing the particles as they pass. Like, that makes sense. And that's how we could understand it, not with hardness and color. It's just so void of what's happening.
And we take those that come out the white aperture, and we send them into a hardness box, hard, soft. And we take those electrons which come out the soft aperture, and now let's send these again into a color box. So it's easy to see what to predict. Black, white. So you can imagine a monkey inside this going, aha. You look at it, you inspect, it comes out white. Here you look at it, inspect, it comes out soft. And you send it into the color box. And what do you expect to happen? Well, let's think about the logic here. Anything reaching the hardness box must have been measured to be white. And we just did the experiment that if you send a white electron into a hardness box, 50% of the time it comes out a hard aperture, and 50% of the time it comes out the soft aperture. So now we take that 50% of electrons that comes out the soft aperture, which have previously been observed to be white and soft, and then we send them into a color box, and what happens? Well, since colors are repeatable, the natural expectation is that, of course, it comes out white. So our prediction, a natural prediction here, is that of those electrons that are incident on this color box, 100% should come out white, and 0% should come out black. Does that seem like a reasonable? So let's just make sure that we're all agreeing. So let's vote. How many people think this is probably correct? Okay, good. How many people think this is probably wrong? Okay, good. That's reassuring. Except you're all wrong, right? In fact, what happens is half of these electrons exit white, 50%, and 50% exit black. So let's think about what's going on here. This is really kind of troubling. We've said already that knowing the color doesn't predict the hardness, and yet this electron, which was previously measured to be white, now when subsequently measured, sometimes it comes out white, sometimes it comes out black, 50% of the time. Okay? So that's surprising.
Yeah, when you say it like that, like, what the fuck? It's so void of meaning. Color. Okay, so it separates incoming electrons are separated by some kind of field, and then half of them, which are all functionally the same when going through this field, go into another separator that influences them, that maybe changes them so that this is just gone. It's just like erases the spin here, inputs a new spin. Like if it's spinning this way, and then you have a field that it passes that it doesn't influence the spin, then it's going to keep going that way. But maybe it's slightly off spin, and so some of them are off the axis of the spin, and so the spin will adjust to the influencing field that it's going through, maybe to basically re-input a new spin into the system. That just means that when it goes through another color field, another field that was the same as the first field, it's as if it's random because they're just back to some different spin again, and so then it just re-influences them to a new spin again that then separates them to half again. like there's so much potential here to what's going on, and just because we predict, oh, they're all white, so they should all stay white, but what is white? See, they're saying that it's like white. Now it's a white electron, but like it's just a spin of the electron, which if you change the spin again and call that new spin another property, like this could go on forever. And every axis, like I'm pretty sure that even said there are as many of these spin properties as there are possible axes. Talk about complex. It's so confusing. Like this is only 2 properties. Imagine if they were like color, hardness, fluidity. I don't fucking know. Because this is some random shit like shape. I don't. It does things that seem like there's something, but they're just relating to the same thing over and over and over again, just measured in a different way. And where the measurement influences the system, it's not like the system goes through and it's just the same as it was before. I mean, these are tiny particles, and we're observing them with techniques that influence their actual mechanics instantaneously to cause them to change. I mean, it's not like a spin must always be the same spin angle. Like, it can change when the environment causes it to change, which basically erases it. And so, like, this would make sense. It's just erasing the previous spin by putting a new spin into it.
Predict the hardness. And yet, this electron, which was previously measured to be white, now when subsequently measured, sometimes it comes out white, sometimes it comes out black, 50% of the time. Okay? So that's surprising. What that tells you is you can't think of the electron as a little ball that has black and soft written on it. Right? You can't, because apparently that black and soft isn't a persistent thing, although it's persistent in the sense that once it's black, it stays black. So what's going on here? Now,
so once it's spinning and then it's in basically a uniform, unchanging environment where it's not going through a magnetic field that's like then yeah, it probably keeps its like momentum and things, keeps spinning the same way until some shit hits it and it's like But to call it color and hardness again.
I should emphasize that the same thing happens if I had changed these to if I had changed this to taking the black electrons and throwing in hardness and picking soft and then measure the color, or if I had used the hard electrons. Any of those combinations, any of these ports would have given the same results, 50-50. It is not persistent.
Because they're just words. Any of these arrangements of different field angles, I assume that's what they're doing, like changing the way the field is gonna erase it. And dependent on if their spin angles a certain way.
In this sense, apparently the presence of the hardness box tampers with the color somehow. So it's not quite as...
This is why it sucks not knowing what they're talking about. To present it without the experiments, like a line. This needs to really like accept what he's saying at face value. I mean, it needs a line of experiments. Here are the experiments where we realize that electrons have color and have hardness and softness. But it's just words. And this is clearly not what they even have. It's not describing the characteristic of them. Like, that's not how physics should work. Like, I understand when other sciences are more open language in terms like that, but, like, that shouldn't be in physics. Color, when it's not color, it's just confusing. Just like all of quantum mechanics. It's confusing. Not because it's right either.
As trivial as that hyper-intelligent monkey, right? Something else is going on in here. So this is suspicious. So here's the first natural move. The first natural move is, oh, look, surely there's some additional property of the electron that we just haven't measured yet that determines whether it comes out the second color box black or white. Right? There's got to be some property that determines this.
Yes.
And so people have spent a tremendous amount of time and energy
not in the input.
Looking at these initial electrons and looking with great care to see whether there's any sort of feature of these.
Are you guys even analyzing how you're influencing these things?
Incident electrons, which determines which port they come out of. And the shocker is, no one's ever found such a property. No one has ever found a property which determines which port it comes out of. As far as we can tell, it is completely random. Those that flip and those that don't are indistinguishable at the beginning. And let me just emphasize, if anyone found such a, it's not like we're not looking, right? If anyone found such a property, fame, notoriety, subverting quantum mechanics, Nobel Prize, people have looked, and there is none that anyone's been able to find. And as we'll see later on, using Bell's inequality, we can more or less nail that such things don't exist. Such a feature doesn't exist. But this tells us something really disturbing. This tells us, and this is the first real shocker, that there is something intrinsically unpredictable, non-deterministic, and random about physical processes that we observe in a laboratory. There is no way to determine a priori whether it will come out.
Yeah, when you freaking don't have enough information. It doesn't mean it's not deterministic. The universe is infinite, and there's always more information possible, and when it gets to this scale, we're just not accounting for nearly enough. It's just too much of an approximation, and so all we can do really is see systems as they function collectively, which creates this like odd mechanics going on, but it's still just particles functioning collectively as a group, where some physical characteristic of them is determining how they go through some change in environment, which these boxes are, and are influenced by it.
Black or white from the second box. Probability in this experiment is forced upon us by observations. Okay, well, there's another way to come at this. You could say, look, you ran this experiment, that's fine, but look, I've met the guy who built these boxes, and look, he's just some guy, right? And he just didn't do a very good job, right? The boxes are just badly built. So here's the way to defeat that argument. No, we've built these things out of different materials, using different technologies, using electrons, using neutrons, using buckyballs, C60. Seriously, it's been done? Okay?
Just assuming that they've fully considered all the ways of thinking about how the observations could be produced.
We've done this experiment, and this property does not change. It is persistent. And the thing that's most upsetting to me is that not only do we get the same results independent of what objects we use to run the experiment, we cannot change the probability away from 50-50 at all. To within experimental tolerances, we cannot change, no matter how we build the boxes, we cannot change the probability by part in 100. Okay? 50-50.
I would love to know how they build the boxes. Alright, man. I can't change it, but what the fuck, man? You build the boxes. Like, I take some. What do? I just, like, go to Lowe's, buy a cardboard box, you know, make it a box, and then, like, shine some electrons through it. Like, something's happened. Oh, my God. It's interesting that there's such a range that has this result, but, like, so what are you guys doing?
And to anyone who grew up with determinism from Newton, this should hurt.
It does hurt to see this, guys. Hurts to see Newton just dismissed for this, for color and hardness. Oh, it hurts. It hurts, dude. What? And just nonsense. Not to say there's nothing here. Just wow.
Right? This should feel wrong, but it's a property of the real world, and our job is going to be...
Not that part that feels wrong. Sure, that's how it goes through the boxes that are probably more specific in how they function than just being boxes that separate color and hardness. But what's happening is classical in nature on a more, like, logical, reasonable, and sensical kind of way of seeing things.
be to deal with it, okay?
True.
Rather, your job is going to be to deal with it, because I went through this already. So, okay? So here's a curious consequence. Oh, any questions before I cruise? Okay, so here's a curious consequence of this series of experiments. Here's something you can't do.
Shit.
Are you guys old enough where you can't do this on television? Oh, Jesus. This is so sad. Okay, so here's something you can't do. We cannot build, it is impossible to build a reliable color and hardness box. We've built a box that tells you what color it is. We've built a box that tells you what hardness it is. But you cannot build a meaningful box that tells you what color and hardness.
Because it's not color and hardness, it's a one field and then another field influencing the particles, and these fields are probably so overwhelming that they just wash away any freaking history of how they were in the past, you know.
An electron is. So in particular, what would this magical box be? It would have 4 ports.
Crazy.
And its ports would say, well, one is white and hard, and one is white and soft, and one is black and hard, and one is black and soft. So you can imagine how you might try to build a color and hardness box. So for example, here's something that you might imagine. Take our incident electrons and first send them into a color box. Okay? And take those white electrons, okay, I'll just draw it this way. Take the white electrons and send them into a hardness box. And take those electrons, and this is going to be white and hard, and this is going to be white and soft. Okay, and similarly send these black electrons into a hardness box. And here's hard and black, and here's soft and black. Okay? Everyone cool with that? So this seems to do the thing I wanted. It measures both the hardness and the color. What's the problem with it? Yeah, exactly. So the color is not persistent. So you tell me this is a soft and black electron, right? That's what you told me. It's the
Not persistent, non-existent, hey, you know. Tomato, whatever, hey.
Here's the box. But if I put a color box here, that's the experiment we just ran. And what happens? Does this come out black? No, this is a crappy source of black electrons. It's 50-50 black and white, right? So this box can't be built. And the reason, and I want to emphasize this, the reason we cannot build this box is not because our experiments are crude. And it's not because I can't build things, although that's true. I was banned from a lab one day after joining it, actually. So I really can't build, but other people can. Okay? And that's not why. We can't because of something much more fundamental, something deeper, something in principle, which is encoded in this awesome experiment. Okay? This can't be done. It does not mean anything as a consequence. It does not mean anything to say this electron is white and hard. Because if you tell me it's white and hard, and I measure white, well, I know that if it's hard, it's going to come out 50-50. It does not mean anything. So this is an important idea. This is an idea which is enshrined in physics with a term which comes with capital letters, the uncertainty principle. And the uncertainty principle says basically that, look, there's some observable, measurable properties of a system which are incompatible with each other in precisely this way. Incompatible with each other in the sense that not that you can't know because you can't know whether it's hard and soft simultaneously. Deeper, it is not hard and white simultaneously. It cannot be. It does not mean anything to say it is hard and white simultaneously.
Yeah, because it's erasing whatever it was with this. For sure, it's something like that. That some field is just influencing them to basically be one or the other again in a different way, where that's because it is spinning so differently, maybe it differentiates.
That is uncertainty. And again, uncertainty is an idea we are going to come back to over and over in the class. But every time you think about it, this should be the first place you start for the next few weeks. Yeah? Questions? No questions? Okay, so at this...
Oh my god, if I was ever in a college physics course. Could you shut up, dude? Trying to teach here. You just keep interrupting with your questions. Oh no.
At this point, it's really tempting to think, yeah, okay, this is just, this is just about the hardness and the color of electrons.
Oh my god. This is just about these nonsensical things we made up to describe something that's not even at all those things. Because it's spin related. Which may or may not even be spin related.
It's just a weird thing about electrons. It's not a weird thing about the rest of the world. The rest of the world is completely reasonable. And no, that's absolutely wrong. Every object in the world has the same properties. If you take buckyballs and you send them through the analogous experiment, and I will show you the data, I think tomorrow, but soon. I will show you the data when you take buckyballs and run it through a similar experiment. You get the same effect. Now, buckyballs are huge, right? 60 carbon atoms. But okay, at that point you're saying like, dude, come on, huge, 60 carbon atoms.
They probably do it slower. In the least.
So there is a pendulum, depending on how you define building, in this building, a pendulum, which is used in...
Maybe a stronger separation technique.
principle which is used to improve detectors to detect gravitational waves. There's a pendulum with a, I think it's 20 kilo mirror. Okay? And that pendulum exhibits the same sort of effects here. Okay? We can see these quantum mechanical effects in those mirrors. And this is in breathtakingly awesome experiments done by Nergis Malvalavala, whose name I can never pronounce, but who is totally awesome. She's an amazing physicist. And she can get these kind of quantum effects out of a 20 kilo mirror. So before you say something silly like, it's just electrons, it's 20 awesome experiments done by Nergis Malvalavala.
Fuck. No dice. So fuck.
Whose name I can never pronounce, but who is totally awesome. She's an amazing physicist. And she can get these kind of quantum effects out of a 20 kilo mirror. So before you say something silly like, it's just electrons, it's 20 kilo mirrors. And if I could put you on a pendulum that accurate, it would be you. Okay? These are properties of everything around you. The miracle is not that electrons behave oddly. The miracle is that when you take 10 to the 27 electrons, they behave like cheese.
So backwards. Accepting that there's this hardness, softness, color, superposition, all this freaking nonsense. And that's fundamental when we clearly aren't even like critically analyzing how the experiments might actually make sense. We're just like, they don't make sense. It's crazy.
That's the miracle, okay? This is the underlying correct thing. Okay, so this is so far so good. But let's go deeper. Let's push it. And to push it, I want to design for you a slightly more elaborate apparatus. Slightly more elaborate experimental apparatus. And for this, I want you to consider the following device. I'm going to need to introduce a couple of new features for you. Here's a hardness box, and it has an in port. And the hardness box has a hard aperture, and it has a soft aperture. And now in addition to this hardness box, I'm going to introduce two elements. First, mirrors. Okay. And what these mirrors do is they take the incident electrons and nothing else, they change the direction of motion. Okay? Change the direction of motion. And here's what I mean by doing nothing else. If I take one of these mirrors, and I take, for example, a color box, and I take the white electrons that come out, and I bounce it off the mirror, okay, and then I send these into a color box, then they come out white 100% of the time. It does not change the observable color. Cool? All it does is change the direction. Similarly with the hardness box. It doesn't change the hardness, it just changes the direction of motion. Okay? And every experiment we've ever done on these guys changes in no way whatsoever the color or the hardness by subsequent measurements. Cool? Just changes the direction of motion. And then I'm going to add another mirror. It's actually a slightly fancy set of mirrors. All they do is they join these beams together, okay, into a single beam. And again, this doesn't change the color. You send in a white electron, you get out, and you measure the color on the other side, you get a white electron. You send in a black electron from here, and you measure the color, you get a black electron again out. Cool? So here's my apparatus. And I'm going to put this inside a big box. And I want to run some experiments with this apparatus. Everyone cool with the basic design? Any questions before I cruise on? Okay. This part is fun. Okay. So what I want to do now is I want to run some simple experiments before we get to fancy stuff. And the simple experiments are just going to warm you up. Okay? They're going to prepare you to make some predictions and some calculations. And eventually we'd like to lead back to this guy. So the first experiment, I'm going to send in white electrons. Whoops. I'm going to send in white electrons. And I'm going to measure at the end, and in particular at the output, the hardness. Okay? So I'm going to send in white electrons. And I'm going to measure the hardness. So this is my apparatus. I'm going to measure the hardness at the output. And what I mean by measure the hardness is I throw these electrons into a hardness box and see what comes out. Okay, so this is experiment 1. And let me draw this. Let me embiggen the diagram. So you send white into. So the mechanism is a hardness box, mirror, mirror, mirrors. And now, whoops, we're measuring the hardness out. So hardness. And the question I want to ask is, how many electrons come out the hard aperture, and how many electrons come out the soft aperture of this final hardness box? Okay? So I'd like to know what fraction come out hard and what fraction come out soft. I send an initial white electron. For example, I took a color box and took the white output. Send them into the hardness box. Mirror, mirror, hard, hard, soft. And what fraction come out hard and what fraction come out soft? Okay. So just think about it for a minute. And when you have a prediction in your head, raise your hand.
Gotta go with the 50-50. And when it's not, be like,
All right, good. Walk me through your prediction.
I think it should be
50-50. How come?
for the colors having bearing on hardness.
Good.
So it's going to go to the hardness box. I would expect it to come out of there. And then once again, when you go to the other hardness box.
Awesome. So let me say that again. So we've done the experiment. You send a white electron into a hardness box, and we know that it's non-predictive, 50-50. So if you take a white electron and you send it into the hardness box, 50% of the time it will come out the hard aperture, and 50% of the time it will come out the soft aperture. Now, if you take the one that comes out the hard aperture, then you send it up here, send it up here. We know that these mirrors do nothing to the electron, to the hardness of the electron, except change the direction of motion. We've already done that experiment. So what do you measure the hardness at the output? What do you get? Hard, because it came out hard, mirror, mirror, hardness, hard. But it only came out hard 50% of the time because we sent in an initially white electron. Yeah? What about the other 50%? Well, the other 50% of the time it comes out the soft aperture and follows what I'll call the soft path to the mirror, mirror, hardness. And it was soft, mirror, mirror, hardness, you know it comes out soft. 50% of the time it comes out this way and then it will come out hard. 50% it follows the soft path and then it will come out soft. Was this the logic? Good. How many people agree with this? Solid. How many people disagree? No abstention. Okay. So here's here's a prediction. Surveys. Oh, yep.
Question. Could you justify that prediction without talking about, oh, well, half the electrons were initially measured to be hard and half were initially measured to be soft, by just saying, well, we have a hardness box, and then we join the beams of electrons together again, so we don't know anything about it. So it's just like sending white electrons into one hardness box instead of two.
Yeah, that's a really tempting argument, isn't it? So let's see. We're going to see in a few minutes whether that kind of an argument is reliable or not. But so far we've been given two different arguments that lead to the same prediction, 50-50. Yeah? Question?
The electrons interact between themselves, like when you get them together.
Yeah. This is a very good question. So here's a question. Look, you're sending a bunch of electrons into this apparatus. But if I take two, look, I took 802. You take two electrons and you put them close to each other, what do? Pew, right? They interact with each other through a potential, right? So yeah, we're being a little bold here, throwing a bunch of electrons in and saying, oh, they're independent. So I'm going to do one better. I will send them in one at a time. One electron through the apparatus. And then it will wait for 6 weeks. And then I'll say, see, you guys laugh, you think that's funny, but there's a famous story of a guy who did a similar experiment with photons. Okay, French guy, and I mean the French, they know what they're doing. So he wanted to do the same experiment with photons, but the problem is if you take a laser and you shine it into your apparatus, then there are like 10 to the 18 electrons in there at any or photons in there at any given moment, and the photons, who knows what they're doing with each other, right? So I want to send in one photon, but the problem is it's very hard to get a single photon, very hard. So what he did, kid you not, he took an opaque barrier. I don't remember what it was. It was some sort of film on top of glass. I think it was some sort of oil tar film. Barton, do you remember what he used? Okay, so he takes a film, and it has this opaque property such that the photons that are incident upon it get absorbed. Once in a blue moon, a photon manages to make its way through. Literally, like once every couple of days. Okay, now, or a couple of hours, I think. So it's going to take a long time to get any sort of statistics. But he has this advantage that once every couple of hours or whatever, a photon makes its way through. That means inside the apparatus, if it takes a picosecond to cross, triumph, right? That's the week I was talking about. So he does this experiment. But as you can tell, you start the experiment, you press go, and then you wait for 6 months. Side note on this guy, liked boats. Really liked yachts. So he had 6 months to wait before doing a beautiful experiment, having the results. So what did he do? Went on a world tour in his yacht, comes back, collects the data, and declares victory because indeed he saw the effect he wanted. So I was not kidding. we really do wait. So I will take your challenge and single electron, throw it in, let it go through the apparatus, takes mere moments, wait for a week, send in another electron. No electrons are interacting with each other, okay? Just a single electron at a time going through this apparatus. Other complaints?
What the fuck is the apparatus? I mean, it's too generic. It's too hardness box. I mean, the mirrors thing is fine, but still the box. Probably some specifics in where they recombine also.
Sorry? Oh, you'll get them. I have a hard time resisting. So here's the experiment. Here's a prediction. 50-50. We now have two arguments for this. So again, let's vote after the second argument. 50-50, how many people? You sure? Positive? Okay, how many people don't think so? Very small dust. Okay, it's correct. Yay! Okay, so good. So.
It's like, what the fuck, man?
I like messing with you guys. So,
Not me.
So, remember.
It's like some fucking crazy shit going on here too. God damn, guys. It's too much, man. Too demanding. I don't know what the fuck.
We're going to go through a few experiments first where it's going to be very easy to predict the results. We've got 4 experiments like this to do, and then we'll go on to the interesting examples. But we need to go through them so we know what happens, so we can make an empirical argument rather than an in-principle argument. So there's the first experiment. Now I want to run the second experiment. And the second experiment, same as the first, a little bit louder, a little bit worse. Sorry. The second experiment, we're going to send in hard electrons, and we're going to measure color at out. Okay, so it's a little hard because we've already done that experiment. The mirrors do nothing to the hardness. So we send a hard electron into the color box. And
Hard, okay. Hard, soft. And then it should be 50-50.
what comes out? Well, we've done that experiment too. Hard into color, 50-50. So the prediction is 50-50. This is your prediction. Is that correct? Awesome. OK. Let us vote. How many people think this is correct? Gusto, I like it. How many people think it's not? All right. Yay. This is correct. OK, third experiment, slightly more complicated. But we have to go through these to get to the good stuff. So humor me for a moment. Third, let's send in white electrons and then measure the color at the output port. So now we send in white electrons, same beast, and our...
And then it'll go back and start.
White hardness, so this basically changes it. So it's 50-50 and then changes again 50-50.
But earlier when we did the same thing without the weird path changing, it came out 50-50 still. So I would say still 50.
Great. So let me say that again out loud and tell me if this is an accurate sort of extension of what you said.
100.
I'm just going to use more words, but it's, I think, the same logic. We have a white electron, initially white electron. We send it into a hardness box. When we send a white electron into a hardness box, we know what happens. 50% of the time it comes out hard, the hard aperture. 50% of the time it comes out the soft aperture. Consider those electrons that came out the hard aperture. Those electrons that came out the hard aperture will then transit across the system, preserving their hardness by virtue of the fact that these mirrors preserve hardness, and end up at a color box. When they end at the color box, when that electron, the single electron in the system, ends at this color box, then we know that a hard electron entering the color box comes out black or white 50% of the time. We've done that experiment too. So for those 50% that came out hard, we get 50-50. Now consider the other 50%. The other half of the time, the single electron in the system will come out the hardness box, come out the soft aperture. It will then proceed along the soft trajectory, bounce, not changing its hardness, and is then a soft electron incident on a color box. But we've also done that experiment, and we get 50-50 out black and white. So those electrons that came out hard come out 50-50, and those electrons that come out soft come out 50-50. And the logic then leads to 50-50 twice, 50-50. Was that an accurate statement of the... Good. It's a pretty reasonable extension. OK, let's vote. How many people agree with this one? OK, and how many people disagree? Yeah. OK, so vast majority agree, and the answer is no. This is wrong. In fact, of these, 100% come out white, and 0 come out black. Never, ever does an electron come out the black aperture.
What is happening though, dude? Like, this is why the details matter.
I would like to quote what a student just said, because it's actually the next line in my notes, which is, "What the hell is going on?" So let's run a series of follow-up experiments to tease out what's going on here. OK, so something very strange. Let's just all agree something very strange just happened. OK, we sent a single electron in. And that single electron comes out the hardness box. Well, it either came out the hardness box or it came out the it either came out the hard aperture or the soft aperture. And if it came out the hard, we know what happens. If it came out the soft, we know what happens. And it's not 50-50, right? So we need to improve the situation. One sec. Oh, hold on one sec. OK. Well, OK, go ahead.
Yeah, I have a question about the setup.
Yeah.
So for the second hardness box, are we collecting both the soft and hard outputs?
The second, you mean the first hardness box?
Or the one,
This
are we
one?
getting, no, the...
Which one? Sorry. This guy? Oh, that's a mirror, not a hardness box. So all this does, oh, thanks for asking. OK, yeah, sorry. This is, I wish I had a better notation for this, but I don't. There's a classic, well, I'm not going to go into it. So remember that thing where I can't stop myself from telling stories? So all this does is just a set of mirrors. It's a set of fancy mirrors. And all it does is it takes, how does that work? So that's an excellent observation. And I'm going to build you now a couple.
As you were measuring it along, right?
Apparently, it's a lot like we were measuring it, right? Because we send in the white electron, and at the end, we get out that it's still white. So somehow this is like not doing anything. But how does that work? So that's an excellent observation, and I'm going to build you now a couple of experiments that tease out what's going on. And you're not going to like the answer. Yeah?
What were the white electrons generated in this experiment?
The white electrons were generated in the following way. I take a random source of electrons. I rub a cat against a balloon, and I charge up the balloon. Okay. And so I take those random electrons, and I send them into a color box. And we have previously observed that if you take random electrons and throw them into a color box and pull out the electrons that come out the white aperture, if you then send them into a color box again, they're still white. So that's how I've generated them. I could have done it by, rubbing the cat against glass or rubbing it against, me, right? Stroke the cat. But any randomly selected set of electrons sent into a color box, and then from which you take the white electrons. Yeah, exactly. Yeah.
Is the difference that you never actually know whether the electron is white or not?
That's a really good question. So I don't want to, here's something that I'm going to be very careful not to say in this class to the degree possible. I'm not going to use the word to know. Good. Measure is a very slippery word too. I've used it here because I couldn't really get away with not using it. But we'll talk about that in some detail later on in the course. For the moment, I want to emphasize that it's tempting but dangerous at this point to talk about whether you know or don't know, or whether someone knows or doesn't know. For example, the monkey inside knows or doesn't know, right? So let's try to avoid that and focus on just operational questions of what are the things that go in, what are the things that come out, and with what probabilities. And
what about operational, like, where are they going through?
The reason that's so useful is that it's something that you can just do, right? There's no ambiguity about whether you've caught a white electron in a particular spot. Now, in particular, the reason these boxes are such a powerful tool is that you don't measure the electron, you measure the position of the electron. You get hit by the electron or you don't. And by using these boxes, we can infer from their position the color or the hardness, okay? And that's the reason these boxes are so useful. So we're inferring from the position, which is easy to measure. You get beamed or you don't. We're inferring the property that we're interested in.
Inferring the color or hardness. Just reiterating that they are meaningless words assigned to just how they function through a field. Whether or not they go up or down.
So it's a really good question, though. Keep it in the back of your mind, and we'll talk about it on and off for the rest of the semester. Yeah?
So what happens if you have the setup and you just take away the bottom right here?
Perfect question. Okay, this leads me into the next experiment. So here's the modification that, thank you. That's a great question. Here's a modification of this experiment. So let's rig up a small, hold on. I want to go through the next series of experiments and then I'll come back to questions. And these are great questions. So I want to rig up a small movable wall. Okay? A small movable barrier. And here's what this movable barrier will do. If I put the barrier in, so this would be in the soft path. When I put the barrier in the soft path, it absorbs all electrons incident upon it and impedes them from proceeding. Okay? So you put a barrier in here, put a barrier in the soft path, no electrons continue through. An electron incident cannot continue through. Okay? When I say that the barrier is out, what I mean is it's not in the way. I've moved it out of the way. Cool? So I want to run the same experiment, and I want to run this experiment in the following, I want to run the experiment using the barriers to tease out how the electrons transit through our apparatus. Okay. So, experiment 4. Let's send in a white electron again. I want to do the same experiment we just did, and color at out. But now with the wall in the south path. Wall in soft. Okay? So that's this experiment. So we send in white electrons, and we send out, and at the output we measure the color. Okay, as before. And the question is, what fraction come out? What fraction come out? Black, and what fraction come out? White. Okay? So again, everyone think through it for a second. Just take a second. And this one's a little sneaky, so just feel free to discuss it with a person sitting next to you. All right, now that everyone's had a quick second to think through this one, let me just talk through what I'd expect from the point of these experiments, and then we'll talk about whether this is reasonable. So the first thing I expect is that, look, if I send in a white electron and I put it into a hardness pass, I know that 50% of the time it goes out hard and 50% of the time it goes out soft. If it goes out the soft aperture, it's going to get eaten by the barrier, right? It's going to get eaten by the barrier. So first thing I predict is that the output should be down by 50%. However, here's an important bit of physics, and this comes to the idea of locality. I didn't tell you this, but these arm lengths in the experiment I did, 3,000 kilometers long. 3,000 kilometers long. That's too minor. 10 million kilometers long. Really long. Very long. Now imagine an electron that enters this, initially white electron. If we had the barriers out, right? If the barrier was out, what do we get? 100% white, right? We just did this experiment to our surprise. So if we did this, we get 100%. That means that any electron going along the south path comes out white. Any electron going along the hard path goes out white. They all come out white. So now if imagine I do this. Imagine I put a barrier in here 2 million miles away from this path. Okay? How does a hard electron along this path know that I put the barrier there? And I'm going to make it even more sneaky for you. I'm going to insert the barrier along the path after I launch the electron into the apparatus. Okay? And when I send in the electron, I will not know at that moment nor will the electron know, because they're not very smart, whether the barrier is in place. And this is going to be millions of miles away from this guy. Okay? So an electron out here can't know. It hasn't been there. It just hasn't been there. It can't know. But we know that when we ran this apparatus without the barrier in there, it came out 100% white. But it can't possibly know whether the barrier is in there or not, right? It's over here. So what this tells us is that we should expect the output to be down by 50%, but all the electrons that do make it through must come out white, because they didn't know that there was a barrier there. They didn't go along that path. Yeah?
Not trying to be wise. Why are you using the word no?
Oh, I was just, sorry, no, thank you. Thank you. That was a slip of the tongue. I was making fun of the electron. So, So in that particular case, I was not referring to my or your knowledge. I was referring to the electron's tragically impoverished knowledge. Okay. Yeah.
But if they come out 100% white, then wouldn't we know then, like know with certainty that the electron is both hard and white, which is like a violation?
Well, here's the more troubling thing. Imagine it didn't come out 100% white. Then the electron would have demonstrably not gone along the soft path. It would have demonstrably gone through the hard path because that's the only path available to it. And yet it would still have known that millions of miles away there's a barrier on a path it didn't take. So which one's more upsetting to you? Okay? And personally, I find this one the less upsetting of the two. Okay, so the prediction is our output should be down by 50% because half of them get eaten, but they should all come out white because those that didn't get eaten can't possibly know that there was a barrier here. Millions of miles away. Okay? So we run this experiment, and here's the experimental result. In fact, the experimental result is yes, the output is down by 50%, but no, not 100% white, 50% white. 50% white. The barrier, if we put the barrier in the hardness path, still down by 50%, and it's at odds, 50-50. How could the electron know? I'm making fun of it. Yeah?
I guess my question is, before we asked how it knows there's a block in one of the paths, how did it know before over there that there were two paths combined?
Excellent. Exactly. So actually, this problem was there already in the experiment we did. All we've done here is tease out something that was existing in the experiment, something that was disturbing. The presence of those mirrors and the option of taking two paths somehow changed the way the electron behaved. How is that possible? And here we're seeing that very sharply. Thank you for that excellent observation. Yeah?
What if you replace the two mirrors with color boxes so that both color boxes
Yeah.
either hard or soft, and then you recombine all four beams and then put it through that last color box?
Yeah, so that's a totally reasonable. So the question is basically, let's take this experiment and let's make it even more intricate by, for example, replacing these mirrors by color boxes. Okay, so here's the thing I want to emphasize. Something that, well, how to say it? I strongly encourage you to think through that example. And in particular, think through that example, come to my office hours, and ask me about it. So that's going to be studying a different experiment. And different experiments are going to have different results. So we're going to have to deal with that on a case-by-case basis. It's an interesting example, but it's going to take us a bit afar from where we are right now. But after we get to the punchline from this, come to my office hours and ask me exactly that question. Okay? Yeah?
So we have a color box, we put it in white, like electrons, and we get 50-50, like random stuff.
Yeah.
How do you know the boxes work?
How do I know the boxes work? Well, these are the same boxes we used from the beginning. We tested them over and over.
How did you first check it if it's working, if it's always trying to maybe just
Well, how to say, there's no other way to build a box that does the properties that we want, which is that you send in color and it comes out color again, and the mirrors behave this way. There's, any box that does those first set of things, which is what I will call a color box, does this too. There's no other way to do it. I mean, I don't mean this because no one's, test.
You can't actually send an electron you know is white.
Oh, sure, you can. You take the electron that came out of the color box. That's what we mean by saying it's white. Well, but that's what it means to say the electron is white, right? It's like, how do you know that my name is Alan? You say Alan, and I go, what? Right? But you might say, look, that's not a test of whether it's present when we ran this experiment and got 100%. We should have been freaked out already. And I want to think through what that's telling us about the electron, the single electron, as it transits the apparatus. The thing is, at this point, we're in real trouble. And here's the reason. Consider a single electron inside the apparatus. And I want to think about the electron inside the apparatus while all walls are out. So it's this experiment. Consider the single electron. We know with total confidence, with complete reliability, that every electron will exit this color box out the white aperture. We've done this experiment. We know it will come out white. Yes? Here's my question. Which route did it take?
Spoiler.
Not a spoiler. Which route did it take? I'm asking you the question. That's why you care. I'm the professor here. What is this? Come on. Which route did it take? Okay, let's think through the possibilities. Grapple with this question in your belly. Let's think through the possibilities. First off, did it take the hardness path? So as it transits through the single electron transiting through this apparatus, did it take the hard path or did it take the soft? These are millions of miles long, millions of miles apart. This is not a ridiculous question. Did it go that millions of miles that direction, millions of miles that direction? Did it take the hardness path? Ladies and gentlemen, did it take the hardness path, the hard path? Well, we ran this experiment by putting a wall in the soft path. And if we put a wall in the soft path, then we know it took the hard path because no other electrons come out except those that went through the hard path, correct? On the other hand, if it went through the hard path, it would come out 50% of the time white, 50% of the time black. But in fact, in this apparatus, it comes out always 100% white. It cannot have taken the hard path. No. Did it take the soft path? Same argument, different side, right? No. Well, this is not looking good. Well, look, maybe this was suggested. Maybe it took both. Maybe electrons are sneaky little devils that split in two, and part of it goes one way and part of it goes the other. Maybe it took both paths. So this is easy. We can test this one. And here's I'm going to test this one. Sorry. Actually, I'm not going to do that yet. So we can test this one. So if it took both paths, here's what you should be able to do. You should be able to put a detector along each path, and you'd be able to get half an electron on one side and half an electron on the other. Or maybe two electrons, one on each side and one on the other. Right? So this is the thing that you'd predict if you said it went both. So here's what we'll do. We will take detectors, we will put one along the hard path and one along the soft path. We will run the experiment and then observe whether and ask whether we see two electrons, we see half and half, or we see. And the answer is you always see one electron on one of the paths. You never see half an electron. You never see a squishy electron. You see one electron on one path, period. It did not take both. You never see an electron split in two, divided, confused. No. Well, it didn't take the hard path. It didn't take the soft path. It didn't take both. There's one option left. Neither. Well, I say neither, but what about neither? And that's easy. Let's put a barrier in both paths. And then what happens? Nothing comes out, right? So no. Okay. So now, to repeat an earlier prescient remark from one of the students, what the hell? So here's the world we're facing. I want you to think about this. Take this seriously. Here's the world we're facing. And when I say here's the world we're facing, I don't mean just these experiments. I mean the world around you, 20-kilo mirrors, buckyballs. Here is what they do. When you send them through an apparatus like this, every single object that goes through this apparatus does not take the hard path. It does not take the soft path. It doesn't take both, and it does not take neither. And that pretty much exhausts the set of logical possibilities. So what are our electrons doing when they're inside the apparatus? How do you describe that electron inside the apparatus? You can't say it's on one path, you can't say it's on the other, it's not on both, and it's not on either. What is it doing halfway through this experiment? So if our experiments are accurate, and to the best of our ability to determine they are, and if our arguments are correct, then that's on me, then they're doing something, these electrons are doing something we've just never thought of before, something we've never dreamt of before, something for which we don't really have good words in the English language. Apparently, empirically, electrons have a way of moving, electrons have a way of being, which is unlike anything that we're used to thinking about. And so do molecules, and so do bacteria, so does chalk. It's just harder to detect in those objects. So physicists have a name for this new mode of being, and we call it superposition. Okay? Now, at the moment, superposition is code for I have no idea what's going on. Okay? A usage of the word superposition would go something like this. An initially white electron inside this apparatus, with the walls out, is neither hard, nor soft, nor both, nor neither. It is in fact in a superposition of being hard and of being soft. This is why we can't meaningfully say this electron is some color and some hardness, not because our boxes are crude and not because we're ignorant, though our boxes are crude and we are ignorant. It's deeper. Having a definite color means not having a definite hardness, but rather being in a superposition of being hard and being soft. Every electron exits a hardness box, either hard or soft. But not every electron is hard or soft. It can also be a superposition of being hard or being soft. The probability that we subsequently measure it to be hard or soft depends on precisely what superposition it is. For example, we know that if an electron is in the superposition corresponding to being white, then there are even odds of it being subsequently measured to be hard or to be soft. So to build a better definition of superposition, then I have no idea what's going on, is going to require a new language. And that language is quantum mechanics. And the underpinnings of this language are the topic of the course. And developing a better understanding of this idea of superposition is what you have to do over the next 3 months. Now, if all this troubles your intuition, well, that shouldn't be too surprising. Your intuition was developed by throwing spears and, running from tigers and catching toast as it jumps out of the toaster, right? All of which involves things so big and with so much energy that quantum effects are negligible. As a friend of mine likes to say, you don't need to know quantum mechanics to make chicken soup. However, when we work in very different regimes, when we work with atoms, when we work with molecules, when we work in a regime of very low energies and very small objects, your intuition is just not a reasonable guide. It's not that the electrons, and I cannot emphasize this strongly enough, it is not that the electrons are weird. The electrons do what electrons do. this is what they do. And it violates your intuition, but it's true. The thing that's surprising is that lots of electrons behave like this. Lots of electrons behave like cheese and chalk. And that's the goal of 804, to step beyond your daily experience and your familiar intuition and to develop an intuition for this idea of superposition. And we'll start in the next lecture. I'll see you on Thursday.
Oh, shit. I mean, it is interesting for sure that this is going on in terms of the observations and how it doesn't match what would be expected. But again, what is going on really when they're saying hardness and soft and color? It's complicated. And to just use words that just confuse the issue. And then now we're talking about superposition. I just don't know. Let's see. Well, I'm gonna keep watching this. Maybe, maybe not. Doing reactions. Maybe, maybe not. Second episode is experimental facts of life. So maybe that'll be more experimental information, which is what I'd really like to see. Not so much the interpretation. I mean, it's interesting. But when... especially that putting a block in the way would have that effect. Wherever that was. It does block.
Still down by 50%, and it's at odds. 50-50. How could the electron know?
I mean, these two experiments are definitely Steelers game. Are definitely interesting. But I want to jump so fast into just being like superposition. Some completely new thing, and there's definitely no way possible in any scenario where we could see how classical mechanics could explain this. I want to say that so fast. That's all. Alright, that's all I got for now, so later.